Good.
Wonderful. Cool. Great. So hi everyone. I'm Zach. I'm the CTO of Aztec, and what we focus on is building privacy preserving technologies on public blockchains, specifically Ethereum, with the end goal of enabling cheap, efficient private transactions and to provide very expressive anonymity for users, so that you can have private wallets, and also eventually, which is the subject of this talk, privacy preserving DeFi protocols. And so I just want to talk a little bit about how it's like the mechanics of how such a system can work on a platform like Ethereum, which by its very nature has to be at some level quite transparent in order to verify the correctness of transactions. Being a bit slow. So yeah, so I'd just like to open by just explaining what exactly are private transactions. What do I mean by that? How do they work? What are the mechanics of them? Because it's not quite as simple as just encrypting user data, because you kind of need there are kind of three types of privacy, which this was actually originally Anna coined these terms when I was talking with her about a year ago, and that's data privacy, user privacy, and code privacy. Where data privacy is the actual values of transacting on a blockchain are hidden, so people know who you are, but they don't know how much you're sending around. Then you obviously have user privacy, where the actual user identities are anonymous on top of this, so you don't know who the sender and recipient of a cryptocurrency transaction are, and you don't know the values contain being transferred, or even ideally the asset itself. And the final kind of ideal goal of what we're building towards is code privacy, where you have a very feature-rich programmable ecosystem like you do on Ethereum with smart contracts, except that those contracts are by their very nature private, so that users, when you transact with the blockchain, people can't see, they can't just see who you are, but they can't even see the address of the smart contract you're transacting with. And that gives you a very strong anonymity set, because effectively all your transactions are kind of pooled together in this encrypted anonymous pool with everybody else. However, if you want private transactions, there need to be some modifications from a traditional transaction because of some of these anonymity requirements. Specifically, a private transfer can't produce any kind of like paper trail or leak some information which allows you to build up a transaction graph. And so your transfers and transactions can't produce linkable database updates. So even things like Ethereum's account-based model is extremely difficult to implement in a privacy-preserving manner without compromises on user privacy, because just in the act of updating somebody's balance, even if that balance is encrypted, is going to leak some information. So the way that we're doing it, and the way which is commonly done, so for example, Zcash is doing it this way too, is by using the Bitcoin's concept of a unspent transaction object. And by that, I mean, instead of users having accounts where, like, with a single value that defines how much they own of a certain token, you instead have discrete notes, where a note represents some defined value of cryptocurrency, and notes have an owner, and a user's balance is just defined as just the sum of all the notes they own. So I could have like a 10 Ethereum note and a 15 Ethereum note, and this construction makes it much easier to perform private transfers using this concept called a joint split transaction, which gets encoded into one of these fancy zk circuits. So just to run through a little bit of how this works, the idea is you have two input nodes where, from the perspective of an observer, these nodes don't leak any information. They're all encrypted. So they have if you could decrypt the node, it'll tell you who owns it and how much they're worth. But unless you have the private key, you can't see that. And so the idea about how you do a private cryptocurrency transfer is you have two input nodes that you own as a user, and you effectively destroy these nodes. And in their place, you create two new nodes where you use zero-knowledge proofs to prove that the values in the encrypted output nodes is equal to the values in the encrypted input nodes. And because the encrypted output nodes can have different owners, that allows you to perform a private transfer. That's how I could send tokens to Anna by destroying 10 Ethereum that I own, and then creating like 2 5 Ethereum notes where one is owned by Anna. That would be a private transfer, as long as nobody can identify it's a little bit more complicated than that, but that's at a high level, that's how it works. And you can get extremely strong privacy guarantees from this kind of construction. And so, but there's a problem with this, which is that zero-knowledge proofs are extremely expensive. They're computationally expensive to verify, and on Ethereum, I think with current gas prices, verifying a ZK snark proof could run you up to $100, which is not particularly scalable if you want cheap private transactions. And so, the way that this is one of the ways that you can solve this, and the way that we're trying to do it, currently doing it, is using these concept of a ZK-Rollup, or I guess in our case specifically, it would be a ZK-ZK-Rollup, because generally ZK-Rollups refer to kind of rolling up public transactions, and what we're doing is rolling up private transactions. So it's, anyway, so the idea is you have, instead of having a zero-knowledge proof which processes one of these transactions where you destroy some nodes and create some nodes in their place, you have a extremely complicated zero-knowledge circuit which verifies a very large number of these zero-knowledge proofs. So the idea is you have this architecture where users can deposit cryptocurrency and withdraw cryptocurrency from this rollup, very much like you would deposit and withdraw into a layer 2. Except that any kind of private sends that you make within this rollup architecture are completely hidden from the world. And because withdrawals are not linkable to deposits, it makes it very easy to obtain a high degree of privacy, even if you want to use your cryptocurrency for some kind of public application, like in a smart contract. Because you can deposit some Ethereum into this rollup architecture, and then at some later date you can withdraw it to a different address, and nobody can link the two. This is also quite a useful method of funding anonymous addresses as well, if you have a need for that. So that's and then just at a high level, how this architecture works is you take that join split ZK snark proof I mentioned before, and you just create another zero-knowledge circuit which verifies a very large number of these join split ZK snark proofs, which is a little bit easier said than done, because verifying zero-knowledge proofs is a very mathematically intensive task, and the zero-knowledge circuits are not traditionally like the proving algorithms for zero-knowledge proofs are relatively slow. So this would take a lot of computational power to perform. But there's been several advances over the last few years which has made this practical at scale. But yeah, anyway, maybe if anybody has any questions about this architecture, I'm happy to discuss after the talk. And then one extra step to this is basically a ZK-Rollup circuit, which is getting a bit ridiculous now. But the idea is it's just a way of massively parallelizing zero-knowledge proof construction. So you, because typically constructing these ZK snark proofs is not very easy to parallelize across multiple devices, but by using this recursive technique that we make that very possible and plausible. The idea is you have a rollup circuit which aggregates 32 private transactions, and then you just have another rollup circuit which aggregates 32 rollup transactions, and then you can build that in a tree-like structure to scale your rollup to extremely large volumes. So that's how you that's how one can enable private transactions on a blockchain like Ethereum. But how does one actually do DeFi, decentralized finance? Because that's a very different kettle of fish. The next step, it quite naturally follows that if you can do private value transfers, can you do something a bit more expressive? Can you actually program the logic in these circuits to create private smart contracts? Because a note in one of these joint split transactions, it can represent more than just token values. In many ways, it functions a bit like a storage slot in a Solidity smart contract. And so those rules around that joint split transaction can be modified because these zero-knowledge circuits are programmable. However, that does massively complicate the rollup architecture because you're adding untrusted code execution into your rollup. And so you need safeguards to make sure that users are protected from malicious actors. So the way that you can do this is by creating this concept of a kernel snark circuit to achieve this kind of concept of code privacy, where you can have private smart contracts you program in the context of a layer 2 rollup, and have users transact with these private smart contracts completely anonymously. The idea around the kernel snark circuit is it contains a record of all of the You have so your private smart contracts are encoded as zero-knowledge snark circuits that you can construct proofs of to send transactions. And what a kernel snark circuit functionally does is it verifies the correctness of one of these single private smart contract transactions. The value of this is that an individual user transacting with this network would construct this kernel ZK snark proof locally on their device, and in doing so, obscures the address of the smart contract they're transacting with. So where are we at so far? You can do programmable private smart contracts. So what about programmable private DeFi? It's a very tempting prospect and something that we very much like to achieve ideally in this year. However, there are problems when you want full privacy. Specifically, the fact that all of the state in your system is private and it's owned by users because it's encrypted and somebody needs to know how to decrypt it. And you can't have public state in your smart contracts, things like the total supply of a token or metrics around which you can construct a liquidity pool, because modifying these global variables will leak information about a user's transaction. And so, for example, if you wanted to make a private MakerDAO, that would be quite difficult on the surface, because if you have one of these collateralized debt positions, they need to be you need some algorithm to determine whether your CDP is under collateralized and then liquidated. But if your CDP is encrypted, how is an algorithm supposed to figure out whether you're under collateralized? And even if it can, how is it supposed to liquidate that position if the only person who knows what that position is worth doesn't want it to be liquidated? So you can do private DeFi like in a very direct manner, in a way that you can, like for example, like port MakerDAO to some private system, or port something like Uniswap. But it's quite difficult because it requires multi-party computations, and you need additional trust assumptions, because you effectively need to replace the function of an algorithm in a smart contract with a decentralized kind of set of users, validators that you need to somehow trust will act honestly and not collude, and use staking incentives to ensure that. So that seems a little bit unfortunate, right? Because that's quite it's not ideal. That's certainly that kind of advanced multi-party computation in the context of ZK rollups on Ethereum is quite some way away. So is there some kind of shortcut that we can do? Is there some kind of cheat to interface to be able to get privacy with existing DeFi protocols? And the answer is yes. And that's basically by interfacing private transactions with public DeFi and acquiring very high degrees of user privacy. So the way that this works, what we're trying to build right now, is that a lot of DeFi protocols can kind of be modeled as time-delayed token swaps, where you don't know the exchange rate between the tokens you're swapping until the point that your transaction is mined. So some examples are like Uniswap, the Uniswap liquidity pool, or trading on Uniswap. These are functionally, you call a smart contract, and you trade token pairs, maybe with some additional logical checks. And so can you create a privacy-preserving bridge to layer one existing DeFi protocols? But the answer is yes. So what you do is you have a ZK-Rollup architecture where you aggregate a large number of user deposits. So the idea would be users can deposit notes of a fixed denomination into a pool. So to give an example, you have like 100 Ethereum that you want to trade into Uniswap. Then you and 100 other people could deposit 100 Ethereum into a pool which will have 10,000 Ethereum in total. And the idea is because all the deposits are of the same value and all of the identities are randomized and anonymous, nobody knows who has actually deposited into the system. And then once you pull that 10,000 Ethereum together, you then interact with the layer one network, and you perform, you call the DeFi protocol as an aggregated construction. And then once your DeFi protocol has, you've sent your transaction and you've received whatever token in exchange that you expect, every user can then withdraw their allotted portion of that, of the process of that transaction, and convert them back into private zero-knowledge notes. And that kind of system can give you a very strong degree of privacy. So this is a little bit how it would work. The idea is inside your ZK rollup, On the left, you have notes of a fixed denomination. They get aggregated together in this aggregation circuit. The idea is then once the amount of value in that circuit is reached a certain threshold, it gets sent across the layer 2, layer 1 boundary to a DeFi bridge contract. And then this DeFi bridge contract will trade with Uniswap or Aave or whatever, and then send the process back into the aggregation circuit. And then the depositors will withdraw their new notes, where, because you know how much, like what percentage of the pool you own, you can trustlessly extract what you've earned without any risk of double spending or somebody taking more than their due. So that's what we're building. And one of the other advantages of this is you get quite cheap interactions with layer 1 because you're sending this expensive layer 1 transaction. It represents a very large number of users instead of just a single user. And this process of depositing and withdrawing into the aggregation circuit, because it happens exclusively on the layer 2, it costs very little gas. It's quite cheap to do. So how do you actually power this private DeFi? Because the concept I've talked about here are quite complicated to pull off in practice. You need some you need quite specialized cryptography, because when I've been talking about these things like kernel circuits and aggregation circuits, these are all zero-knowledge circuits that perform an extremely large amount of mathematical number crunching. Specifically, they're verifying the correctness of hundreds of zero-knowledge proofs, which is not trivial to do. And so this is where the latest R&D that Ariel and I, our chief scientist, have been working on is going to hopefully come in quite handy. So PLONK is a universal snark proving system that Ariel and I published in 2019, and we haven't been idle since then. We've been working on it and refining it and improving it, and also taking in all of the brilliant ideas that have come from the wider cryptographic community to improve this thing. And we've developed what we're calling Ultra PLONK, which is what we think it's pretty much the state of the art when it comes to universal proving systems. It allows you to relatively efficiently verify the correctness of a zero-knowledge proof inside a zero-knowledge proof, so this concept of recursion. And you can do it on Ethereum today without needing access to advanced cryptographic primitives that aren't supported by the Ethereum protocol. And you also have constructions like things like you can represent random access memory inside your circuit. So you can have things like dynamic arrays, which for a typical programmer probably sounds extremely trivial. I mean, dynamic arrays, you know, we've had those since the 1960s, back when people were programming in COBOL or in regular computers. But this is something which is extremely hard to achieve inside a zero-knowledge circuit, because what you're effectively doing with zk-SNARKs is you're taking like an imperative computer program and trying to turn it into some algebraic formula, some mathematical representation. And so things like array access is not particularly easy to do, but we've got a way to do it. And that, along with other techniques, is why we think we can build this privacy preserving system. And so, yeah, anybody who's interested in zero-knowledge proofs who works in this field, this is just a table of the constraint counts for our new proving system. And anyway, yeah, happy to go back to that if anybody has any questions. We're also building a private smart contract domain-specific language for programming these circuits, so that you can program in a natural, high-level, relatively natural, high-level language that then compiles down to a zero-knowledge proof without you having to worry about the cryptography behind it or having to understand the cryptography yourself. And the idea is that this can be used to create very feature-rich programmable private smart contracts. So you can have a lot of logic that encodes the correctness of your private transfers. So we're releasing that this week, I believe. Actually, we're releasing an alpha of it. So yeah, we'll be publicizing this fairly soon. And yeah, if anybody wants to have a go. And this is what we're building, releasing next week. It's called zk.money, which is a fully private crypto payments using our ZK-Rollup technology, which we're deploying on mainnet this week. So it's been for us, it's been quite a long development process, but it's finally hopefully going to arrive next week. And yeah, this is aggregated private crypto Ethereum transactions on Ethereum using our ZK-Rollup technology, completely trustless, with one of the strongest, with an extremely strong anonymity set, where we're aiming to get the average cost of a private transfer down to about 15,000 gas. So very competitive with regular Ethereum transactions. So yeah, that'll be coming next week. And longer term, what we're aiming for is pretty much just build everything that I've just talked about. So halfway through this year, we're going to be building this aggregation circuit and this ability to interact privately with existing DeFi layer 1 protocols, and to do so relatively cheaply. And then finally, next year, we will be publishing our full vision of the Noire programming language and have the ability to directly program circuits inside our smart rollup architecture. So yeah, that's pretty much that's pretty much everything I have to say. That's kind of our roadmap for getting privacy into DeFi. Yeah, thanks for listening. And yeah, if anybody has any questions, I'd be happy to answer.
This is so exciting. I actually have a question for you about the rollout. Like you have this plan to roll this out next week on mainnet, but like, are you deeply affected by the crazy gas prices?
Like, just not gonna lie.
It's a tough time right now.
Yeah, we've had to reset our expectations. We were hoping to say that you could do a private transaction for 10 cents, but now it's merely the cost of a regular Ethereum transaction, which is it's unfortunate, but it's something we're working on. I don't think we're as badly affected because I think the value there's the people who will use our protocol desire transaction privacy quite strongly, given that it's the price of it is going to be pretty much equivalent to an existing Ethereum transaction. It means that anybody who wants privacy will hopefully be able to afford it. But yes, it's not going to be. We're not yet at the point of extremely cheap private transactions. Hopefully, that's coming later this year.
If anyone has any other questions, you can actually leave them in the hop-in. Oh, there is one here. Yeah, is Noire DSL named after the French cabinet Noire?
No, it's not. It's just it's named because it's the God, I feel so uncultured. The French for black, and because what we're doing is privacy and shielding transactions from the public. Okay. We thought it was very appropriate.
Although now I'm curious what this cabinet Noire is. Maybe we can look that up after. John asked, do you see a path to achieving similar functionality but without a trusted setup?
Yes, although it would require the Ethereum protocol to add support for new cryptographic primitives, and also probably Ethereum. Certainly, when Ethereum 2.0 comes online and the cost of call data drops, then they'll be very plausible. So the zero-knowledge proving system that we're using, which the ones that most people are using these days, things like PLONK or Marlin, they're very amenable to being ported over to proving systems that don't require a trusted setup. However, the trade-off of doing so is that the proof sizes scale to hundreds of kilobytes up to even a megabyte. And at that data size, it's extremely expensive to process one of those transactions on Ethereum. Because adding 100 kilobytes of call data it costs millions of gas, which with current gas prices is quite punishing. Whereas using a trusted setup, the circuit size, the proof size is only like 1 kilobyte. So what we've got at the moment, we hope, is a bit of a halfway house where we do require a trusted setup, but it's just one trusted setup for every single circuit that gets programmed. So we won't need to repeat it. But
is that the same? Are you using the same kind of parameters as you created in the ignition ceremony, or are you making a new one for this?
No, we're using the ignition one.
Cool.
Yeah, it was quite fortunate. We created our ignition ceremony for a very different protocol, and it just so happened that we could reuse it for PLONK.
Very cool. John Smith, the person who asked about the cabinet Noire, actually answered what that is. So maybe I can tell you. It was apparently used to read encrypted mails for the king's court, a dark room where the cryptographers of that day secretly worked on private letters.
That is fantastic. I wish we did name it after cabinet Noire. Now that's brilliant.
Isn't that neat?
Yeah.
Yeah, I think you should probably call. If anyone asks again, you'll be like, actually.
Yeah.
Okay. Oh, there's one more question here. Are you considering releasing on top of like L2, maybe an OVM, like the optimistic rollup, instead of layer 1? So working, I guess, wow, that would almost be like a ZK-ZK-rollup on top of an optimistic rollup. I think that's what that would mean.
Yeah, yeah, absolutely. We're considering it. Certainly, if there's like our tech is any OVM that supports smart contract execution, we can quite very easily port a protocol to, and that's certainly something that we're exploring right now.
Cool.